This is the disinfection part of the pre-certification training. If you see things in red or highlighted, that may mean that you might see it as a test question. Pathogenic, they cause disease. They're organisms that cause disease. So that's what a pathogen is. There's organisms that don't cause disease or non-pathogenic. The process to kill pathogenic organisms is called disinfection. There's bacteria. This is Shigella. There's you'll notice that the common factor in these is they're caused by human or animal feces. E. coli causes gastroenteritis. So you see these different diseases caused by bacteria in the water. Viruses also, there's hepatitis. Again, human feces causes that. You got infectious hepatitis, gastroenteritis, upper respiratory problems, and so they're all caused by feces in the water. Protozoans like Giardia, Cryptosporidium, they're caused from human or animal feces. Cryptosporidium, they had in Milwaukee in the 90s, killed about 140 or so people when it got in the water. It wasn't filtered out. And so these are things that we deal with in the water industry. There's methods of detection. There's the membrane filter test, multiple tube fermentation test, and cold alert. Disinfection is a process to kill or inactivate most of the microorganisms in the water. The operative word is most, and if you think about that, it doesn't sterilize it. So the disinfection process, most humans can their bodies can fight off a lot of these things, but when you get an abundance of them, or if your immune system is down, that's when you get sick. There's several ways to disinfect, but chlorine is the most popular because it leaves a residual in the system and they can monitor it. If there's a residual in the system, generally the bacteria is kept it's either clean or there is a residual of chlorine left there to kill any bacteria that might enter the system. So it's the most popular. There's other methods that include UV and ozone. Obviously UV, which is done through light, does not leave a residual. Ozone leaves a slight residual as it leaves, but it dissipates quite rapidly. This is heat boiling. There's radiation like UV light. There's chemical, bromine, ozone, chlorine dioxide. There's iodine. All of these are ways to disinfect. If you look, the oxidizing reagents, the potential, the highest one is ozone. If you've ever been near a lightning strike or had one go close by, you can smell that ozone in the air. Permanganate has 1.67, and then you got chlorine that's like down here at 1.36. Hypochlorite has 0.94 oxidizing potential. What is ozone? It's a natural component of the Earth's upper atmosphere, where it is primarily formed photochemically. Like I say, it doesn't leave a lasting residual. Ozone simply means the ozone molecule contains 3 oxygen atoms. They a lot of times call it O3. It's nothing more than another molecular form of oxygen. The chemical symbol for oxygen is O2. So adding that extra atom to that chemical symbol, it makes it O3, and so it has a higher oxidizing potential than regular oxygen. Ultraviolet light is through it can be sunlight, it can be through bulbs, lamps, and that create this UV light. It's the only method of disinfection that doesn't alter the pH of the water or the taste, or affect the chemical composition of the water. So UV is popular, especially with disinfection byproducts and trihalomethanes, and that UV is popular because it doesn't create those trihalomethanes and disinfection byproducts. As the water passes through these UV lamps, it's disinfected. It operates best when the suspended solids are less than 10 to 15 parts per million and the turbidity is less than 5 to 10 NTUs. Gas chlorine, you need to know that it's heavier than air. If you've ever been around a gas chlorine leak, you can see the the cloud. It's a yellowish green type cloud that hangs near the floor. It kind of floats there. It's gas chlorine used primarily for disinfection. The boiling point, if you look at that, is a minus 34 degrees centigrade and a minus 29 Fahrenheit. So the liquid out of a chlorine cylinder expands 460 times. Chlorine also lowers the pH of the water, which makes it more aggressive. When you're changing your cylinders, you should shut the gas at the cylinder off first because you want to evacuate the chlorine that's in the lines and the pigtails. This is a DPD kit here. That's how you measure the chlorine in the water. You can see the different colors of pink, and the lighter the pink, the less the concentration, and the deeper the pink, the more the concentration is. You should, if you have an SCBA, which is a self-contained breathing apparatus, it should be stored away from the chlorine building so you don't have to go inside and get hit with chlorine gas to get it. So you should store that away from the building. There's three different types of chlorine. There's calcium hypochlorite, which is a powder, and there's a question on the test that asks what HTH stands for, and that's a high test hypochlorite. It's a dry powder, and it's 65%, so when you calculate your dosing, you need to figure that 65% because it is a weaker strength of chlorine. Sodium hypochlorite is liquid. The bleach that you have in your home is about 5%. There's a T-chlor that's 15%. When you're considering your calculations, when you do your chlorine calculations, you should consider figure them at 100% purity. It's extremely corrosive with water. It's compressible. Like I say, because it's 2.5 times heavier than air, it does hang towards it does float around the floor. This is the color of it in this beaker here. And it has to meet NSF approval to use it for water applications, for drinking water. Chlorine terms. Free chlorine is a chlorine that's remaining after chlorination. The total chlorine is the sum of combined and residual chlorine and free available chlorine. The demand is the difference between the chlorine added and the remaining chlorine. Pre-chlorination is chlorine injected prior to treatment. This is not done because of the organics in the water cause disinfection byproducts. So it's usually used in post-chlorination situations where it can get into the system and maintain a residual. Break point is the point of chlorine that's added to the water until the demand is satisfied. So once the demand has been satisfied, then that's called break point, and then after that it's free chlorine. Here's a picture of the graph. As the chlorine is introduced into the water, it comes up here, the graph, and then it starts to drop off. As it starts killing the bacteria off, this is where the demand is on this side of it, and then you hit break point. This side of break point is free residual. That's what is in your system after disinfection has taken place. So there's a question on the test that says that if you have a customer call complaining of swimming pool odors, what's the most likely remedy for that? And that's because you're on this side of the graph, you could have heavy smells of chlorine in your system at this point. And so what you need to do is add more chlorine to reach break point. So a lot of times, you know, you're going to want to take a free chlorine residual, and you're going to want to take a total residual if you get those types of complaints. But on the test, if the swimming pool one says you need to add more chlorine to reach break point. There's gas, there's dry or direct feed, solution feed. The gas is mixed with water under pressure, and the vacuum feed pulls the chlorine through the system. Hypochlorinators, dry or liquid. This is a liquid type setup. You can see this is we talked about this in the pumps one. This is a double diaphragm pump here, and this is the liquid. Systems with low flows for emergencies, intermittent seasonal use, things like that, use these hypochlorinators. It talks about cleaning the parts of these of the equipment, and you use an acid solution to clean them. You don't scrape them or Use sandpaper, emery cloth, things like that. You use an acid solution because you don't want to damage the parts. You notice here, this is an ammonia bottle. This is how you test for leaks around your cylinders. This is an air intake. So you kick this fan on, this air intake opens up and it pulls fresh air from outside and it pulls it through the room through this exhaust fan. So you've got an exchange of fresh air. So if you look, this fan is near the bottom of the room, and that's because chlorine will hang at low places. So when you kick this on, this fresh air will go through and it will exhaust the chlorine out of the room. Let's see. And this is again, this is another shot of that. These you notice these are chained down. There's a wrench on there so you can shut it off fast, and then again the fan is near the floor to exhaust the gas out of the room. Chlorine scales, if you look here, this one here is full. You can see the on the scale here, this is about half full, and again they sit on scales, and that's how you can tell you know what your feed rates are, how much chlorine you're using each day. This is a typical hypochlorinator, and you've got your diaphragm pump on top here, and this goes down inside there. There's a foot valve down in the base of that and a strainer, and this pumps and it's injected into the system at this point here. This is a good hypochlorinator setup. I like this because it's got this graduated glass here, and you can actually put the chlorine or whatever chemical you're feeding in it, and then you can time that, and you can see if your pump's actually pumping what it should. And you can see the barrel of chemical down here. Again, this is a good hypochlorinator setup with the graduated glass over there, and it's used for feeding liquid hypochlorite into the system. Safety hazards: when chlorine comes in contact with petroleum and other combustibles, it can cause a spontaneous combustion, and you can get an instant flame with no spark. So you got to be careful what you put around that. We put some steel wool in a beaker and put chlorine gas in it, and it ignited it. It started a spark. So the gas is quite dangerous if you're not careful with it. When it's mixed with hydrogen sulfide, it reacts to cause sulfuric acid, which is hydrogen sulfide. You could get that in some of your water conditions. Chloramines is a reaction between chlorine and ammonia, and how I remember that is you got chlorine on this side and then amines over here, which is ammonia. So chloramines is a reaction between chlorine and ammonia. When this happens, it weakens the strength of the disinfection properties of chlorine. So you gotta always remember that anytime you have something in the water, chlorine's probably going to react with it, and it's going to weaken the strength of your disinfection properties. Chloramination. We don't do this in Utah, at least to my knowledge. I don't know of anybody that uses chloramination, but that's when you actually are creating this reaction between chlorine and ammonia. It's used to reduce taste and odors, but it's a weaker disinfection than chlorine. Actually, because it's reacting with the ammonia, so it does weaken the strength of disinfecting strength of chlorine. Disinfection byproducts, TTHMs are total trihalomethanes. There's a combination of free chlorine and organics. The warmer temperatures and pH form the THMs faster. Reducing agents readily give up electrons. They're opposite of the oxidizing agents. They also react with chlorine. Ferrous, nitride, hydrogen sulfide are examples. They suspended solids, and again, chlorine reacts with hydrogen sulfide to form sulfuric acid. There's 5 principles of chlorine disinfection: concentration, contact time, temperature, pH of the water, foreign substances in the water. Concentration and contact time. If chlorine concentration is decreased, then the contact time must be increased. What that's saying is you got to give the chlorine time to break the cell wall of the bacteria down. Longer detention times would have higher bacteria kill rate. So the longer the chlorine is in contact with the bacteria, you get a better kill rate. When chlorine leaves the facility, it's got to have a minimum of 0.2 parts per million by rule, and then you have to have a measurable residual throughout the system. So what that's telling you, that if you have a 0.2 and you can maintain a residual, that's fine. But if you can't maintain a residual throughout the system, then this 0.2 needs to be raised. What chlorine does, it penetrates the cell wall. And detention time is actually, there's a formula on your conversion sheet that has this, is equal to the volume divided by the flow rate. Temperature, at lower temperatures, the bacteria kill rate's lower. It's like when you put bleach in your laundry to bleach your whites, you put it in hot water because chlorine reacts better in warm or hot water. So if you have cold water, like in the wintertime, you may need to adjust your chlorine dosages because you don't have enough chlorine. It's not in contact with enough. So you use a stronger chlorine residual to kill the bacteria because you don't have that warmer water like in the summer. Higher temperatures cause the faster rates of total trihalomethane, so that's another important part of disinfection. pH, you should check the pH routinely. If the pH of the system is raised for corrosion control, you need to probably increase your chlorine dose because it's going to react with it. Chlorine is most effective at neutral on the pH scale. That's a 7. Turbidity, chlorine is only effective if it comes into contact with bacteria. If you look at this, these beakers full of turbidity in the water, what chlorine does is it comes in contact with the bacteria, it breaks the cell wall down, and then it strips the skin off, and then the bacteria dies off. The one thing about turbidity is that the bacteria can hide behind it, and so the chlorine will not come in contact with it. So it's kind of like in the middle of the summer. I use this analogy that in the middle of the summer when it's hot outside, I'm looking for a shade tree because I don't like that sun beating down on me when it's 100 degrees outside. It's the same thing with bacteria. The bacteria is looking for something to hide behind, and so this turbidity in the water, the dirt and particles in the water, the bacteria can hide behind it so the chlorine doesn't come in contact with it. It also chlorine reacts with organic matter, and and ammonia, and that's what causes disinfection byproducts and chloramines. The turbidity can mask the bacteria. This is a picture of a chlorine system. You got your tank here, your regulator. The chlorine comes through the regulator, goes through here, this feed rate. This is your pounds per day, and then it comes out and it's injected into the system through an injector. The gas chlorine vacuum regulator, this is a picture of one here. Again, you can kind of see the graduated glass here that has your pounds per day feed rates. Here's your ejector, and it keeps the water moving. There's a check valve here that keeps the water from getting into the chlorine system. You don't want to get chlorine in your water into your chlorination system. 150-pound cylinder. The maximum feed rate for a 150-pound cylinder is the proper setting for that is upright, and the maximum feed rate is 40 pounds per day. A yoke is the connection between the tank and the regulator or gas piping. This is a chlorine cylinder valve, and you always want to inspect the cylinder valve before you open it. Check the fittings with ammonia gas to make sure there's no leaks around it. Once a connection has been made, the valve should only be opened a quarter of a turn, and check for gas leaks. You want to always close the cylinder valve first to allow the gas to drain from the pigtail. Always close the cylinder valve first. That is a test question that a lot of people miss. You don't close it at the manifold. You always close it at the cylinder because that's the source, and then it allows the gas in the pigtails to drain off the lines. Fusible plug. It's a lead plug that's made to melt. So if the pressures get too high, like I said, this thing boils at a -34 degrees. it melts between 160 to 165 degrees, so there is a test question on that. And so you always want to keep the cylinders away from direct heat. You don't want to store them outside in the summer where they have direct sunlight on them. On hot days, you could essentially that plug could melt and you could have a leak, the chlorine being released off of the cylinder. When the feed rates exceed the maximum, icing can occur, and I've seen that happen where we had developed a block of ice around one of those because the feed rate was too high. For higher feed rates, you can manifold them. For example, 150-pound cylinders, 40 pounds per day, but you can manifold them and you can feed 120 pounds per day, 40 out of each cylinder. They're filled 85% full for expansion. That's put in there for a reason. That 15% at the top with no liquid in it. On a ton cylinder, it has 6 fusible plugs, 3 on each end. When a ton cylinder is full, it's approximately 3,550 pounds. You need to know that on the test it says how much does a ton cylinder weigh, and one of the wrong answer is 2,000 pounds. They figure, well, it's a ton, it's 2,000 pounds, but they weigh almost 1.5 tons more than a ton when they're full of gas. If you look here, you can see your this piping here, and this is in a vertical position. The top valve pulls gas off the top, and then the bottom valve pulls the liquid off the bottom. You've got 6 fusible plugs on each end, and they're also a protective part of that, and they're also filled 85% full for expansion. Chlorine cylinders, a rupture is the most serious type of chlorine leak. And if you have a leak that's down on the cylinder, you want to rotate that leak so it's on top. Remember that liquid chlorine expands 460 times, so you want to rotate this cylinder so that it's coming off the top where there's gas. Oops. So that's the maximum feed rate is 400 pounds per day on a ton cylinder. Here's some ton cylinders. They need to be strapped down, and they're on scales. This is a Rotometer. This is a grounding strap. You can see how this is all set up here. This is actually pulling the gas off the top. You got your valve here that pulls the liquid off the bottom, but this is the setup here. Here's a fusible plug right at that point there. This is a Rotometer. This is your pounds per day where that ball sits. These are your cylinders. This tells you the weight that's left in there. It helps you calculate your use of your pounds per day. This is an injector that is used to eject the chlorine gas into the line. This is an evaporator, and if you use liquid chlorine off of the cylinder, the liquid chlorine is pulled into this cylinder here. There's a water jacket on the outside. This is your heating element down here. This heats up and it keeps the water hot inside of here, and so the minute this is hot, this cylinder is kept hot, and so when this liquid chlorine comes through here and hits this heated cylinder here, it immediately turns to gas and then it goes out. So that's what an evaporator is used for. Here's a cylinder being pulled off of a truck. You can see the 3 fusible plugs. There's 3 on each end. A lead gasket. You never want to reuse a lead gasket. Never stack lead gaskets on top of each other. And you never want to tighten them more than 1/2 to 3/4 of a turn after you make contact with the lead. You can deform that gasket and get a leak across a brand new lead gasket if you crank down on it too much. Alright, let's see, I don't know what that's doing up there. Okay, preventive maintenance. After 1 year of service, your preventive maintenance kit should be installed. Always use new diaphragms. O-rings, never reuse parts. The O-rings need to be made out of Viton. If you use a Buna-type rubber, it will turn to paste. Chlorine will do that. You want to use a special grease to lube the rings because they're easier to pull your parts apart and they're easy to remove if you use this special grease. Don't use just any grease. They make a special grease for putting those O-rings in. Always want to inspect the PVC parts for cracking or damage. And again, you use an acid solution to clean your pump parts. Chlorine train cars, they use a C-kit for those. This is a chlorine leak from a train car. You can see how the chlorine gas hangs towards the bottom of that rail yard. So here you've got, this is a B kit. This is for a ton cylinder. This is a B kit here. And then there's an A kit for a 150-pound cylinder, which is this one right here. This is a repair kit for a sidewall leak in the 150-pound cylinder. This puts pressure on this patch here. This is a ton cylinder, a valve repair kit. You can see how this is adjusted inside of this the cylinder end here. And they put this over the leaky valve to seal that off. Canister type masks should only be used for escape purposes. I've been in a chlorine area with one of these on. You cannot smell chlorine. They do filter the chlorine gas out, but the problem with that is the chlorine gas displaces the oxygen in the room. And so you want to get out and put an SCBA on if you have a chlorine leak. Don't stay in the room because you might suffocate due to lack of oxygen. You won't be overcome from chlorine, but you will suffocate, so be careful. Self-contained breathing apparatus. You should never enter a room suspected of a leak without an SCBA on. PVC piping, only corrosion-resistant piping should be used. Schedule 80 is not recommended for use with chlorine. I got that from a pipe manufacturer. They say you should use this polyvinylidene fluoride type piping. You should replace Schedule 80 out every 5 to 10 years. And the Chlorine Institute sets standards for that. Chlorine valves should be replaced or maintained annually. This is you might see this on the test. So you want to have those looked at. We had a valve company look at ours periodically, annually. Okay, that's that part of the system, the first half. We will go to the second half of the presentation.